triple integral. We want to evaluate the integral from 0 to 1, 0 to x, and 0 to xy of x dz dy dx. The best approach I take is this. I integrate this and then I take that limit. If I integrate y, I use that limit. And if I integrate x, I use that limit of integration. So z, it will be 0 to 1 and then 0 to x. It will be xz, then 0 of xy, dy dx, and that will give me from 0 to 1 and then from 0 to x. If I substitute xy where there will be z, it will be x squared y dy dx. Remember that we are integrating with respect to z, so x is treated like it is a constant at that point. The next step now, I integrate with respect to y, so it will be equals 0 to 1, and it will be x squared y squared over 2, and then 0 to x dx, and that will give me 0 to 1. Where there is y, I substitute with x, so it will be x squared times x squared over 2 dx. And I know this is equals to, or that is equals to x to the power 4 divided by 2. So the next point is to do the last integral, and this gives us equals to x to the power 5 over 10, and the limit is 0 to 1, which is 1 over 10. Another example is the integral from 0 to 3, 0 to 2, and then 0 to 1, x plus y plus z dx dy dz. Again, I move outward. That means I start with the internal, both from the limits of integration and the integral with respect to, and that gives me 0 to 3, 0 to 2. I want to integrate with respect to x, which is x squared over 2 plus xy plus xz. And then I'm going to substitute the limits of integration from 0 to 1. So whenever there is x, I'll put 1, and therefore it is integral from 0 to 3, 0 to 2. When x is 1, it will be half plus y plus z, then minus 0, so I'll ignore that. So if I integrate with respect to y, 0 to 3 is half y plus y squared over 2 plus yz 0 to 2. And then I have dz. And therefore, again, that gives me 0 to 3. Where there is y, so it will be 1 plus 2 plus 2z dz, which is equals to 0 to 3, 3 plus 2z dz. And that takes us to our last point, which is equals to 3z plus z squared and 0 to 3, which will be 9 plus 9, and the answer will be equals to 18.